Okay, thank you. So, right, I was asked to talk about some of this work that I completed with over a few years with Jacob Bedrossian and Alex Blumenthal, and basically the goal was to study sort of the behavior. The main motivation, let's say, was to study the behavior of some passive tracer being advected in a typical, although let's say smooth fluid flow, with the motivation of it being something that came from like the Navier-Stokes equations, or something like that, although it can be more general. But in particular, if there's some sort of a little bit of randomness in it to kind of kick things up a little bit. So I'm going to show you a video of this. So this in particular is a simulation on the 2D periodic box. There is a 2D stochastic Navier-Stokes in the background. Of course, it's Galerkin because that's what we're simulating. And here is an initial tracer concentration. It means 0. So see on the scale, red is positive, blue is negative. And okay, the flow is quite turbulent, but it's smooth. And what you'll see is that we're interested in looking at these kinds of flows. I mean, they're pretty complicated, pretty messy. Of course, you can imagine cranking up the Reynolds number arbitrarily high, and you see that you introduce lots and lots of small scales, lots of stripes. There's a kind of almost like a stable, unstable manifold foliation that's being showed that's sort of moving around. There's a lot of coherent vortices. Inside the coherent vortices, you get structures that kind of tend to keep scalar trapped inside of them, but every so often they get destroyed and the scalar goes away. So basically, I want to understand the long-time behavior of this system in a mathematical setting. Of course, we can consider more general systems in this. Okay, that's it. That's my topic. Okay. Okay, so I'm going to start out with a quite long, I think, general discussion about just the advection-diffusion problem and sort of what are the questions you might want to answer about it, and then in particular, how can you look at these from a dynamics perspective, and then what tools do you have to actually solve them, and then what is it that we did? So let's just consider a very general setting. Suppose UT is some divergence-free velocity field. I mean, just to keep it simple, or let's say general, but some compact Riemannian manifold. Okay, but if you like, I mean, just think the torus or something like that, and D equals 2 or 3 dimensions. Okay, so subscript T here is how I'm typically denoting time dependence, because I'm sort of coming from a stochastic analysis standpoint, so don't confuse it with a time derivative if you're really a PD person. And so we're thinking like, in a situation, okay, I have this typical velocity field, it's describing some kind of fluid flow. And of course, if the manifold has a boundary, I want the fluid to be moving tangent to the boundary. So it has something like this, or it could be 0 on the boundary, depending on the exact situation. All right, but it could be quite complicated. And what I'd like to understand is the advection-diffusion equation. So that is now this is the equation that describes the advection of some function, some scalar function that is sort of getting dropped into the flow, and then just like the video I showed you, it's getting transported and moved along the streamlines of the flow. Now typically, because especially for divergence-free flows, this thing gets very tangled up very quickly and starts to generate lots of high frequencies. Okay, so there are a number of questions we may want to ask, but let's say in general, is to study the long time behavior of this. Now, I'm being a little sloppy here, I should say. The velocity here, I'm only going to be working in a setting where we're thinking of velocity fields to be smooth. I mean, okay, they can be Sobolev regular or something like this, but smooth in general. And we want to study the long time behavior of this equation. Okay, and what do I mean by that? Well, there's a lot of questions you could ask about studying the long time behavior. One of the things, especially from a PD standpoint, might be that you want to study norm growth. Okay, so for instance, you may want to understand whether if I measure the regularity of this scalar at time t for some Sobolev regularity, which is positive, does it go to infinity? So this is kind of synonymous with at least locally somewhere in the equation or in the flow, there are gradients being generated.
Even if the flow is uniformly smooth.
Even if the flow is smooth, exactly. So,
uniformly smooth in time, right?
That's right. Yeah, it could be, you know, all you need is just a few, I think just a couple Stokes functions, which are just, you need to squish things and generate gradients. So this happens even if I have one fixed flow, which has a saddle, for instance, or even if it just has shearing between, if it just wanted to go to infinity. Pretty much most flows do this unless they're like isochronal or something like that. The other thing you might want to understand is sort of, and again, I'm going to state this in a PD language just for a second, is what you might call mixing. Stated perhaps a little bit more strongly than needed to be, and that is, let's say, decay in negative regularity noise. Okay, but you could replace this with a more general weak convergence, let's say. So take any test function of suitable class. Show that this goes to 0 as t goes to infinity.
And you're considering a kappa 0 case for these questions. For the norm growth.
That's true. Yeah. Okay. Right. That's a good point. So for norm growth and for both of these, yeah, I should mention this is typically the thing you want to consider for kappa equals 0, because
Yeah. Otherwise,
this doesn't usually happen, and this always. Right. So, but okay. So the question you may want to ask instead is. Okay, I'll be a bit more precise about this too. When kappa is greater than or equal to 0, you may want to understand actually in general rates at which these things happen. So, okay, this may not go to infinity. This will certainly still go to 0, but understanding the rate at which this goes to 0, or in fact, this will also likely go to 0. Understanding the rates at which they go to 0. In fact, one thing you can show in kind of a general sort of setting is that if my velocity field's not too crazy, both of these things asymptotically tend to the same exponential rate if one of them is exponential. So the rate at which these things decay. And when I say sort of relative to kappa, is an interesting question. So this falls under often what's referred to as enhanced dissipation. So right. So at this pure advection level, so let's work. Work without diffusion. This equation, just the pure advection equation, is naturally described very cleanly in terms of flow of diffeomorphisms. Okay, typically, at least in fluid mechanics, referred to as the Lagrangian flow. So specifically, I'm going to define a flow of diffeomorphisms, phi t, u. which maps from the manifold to itself, and it belongs to S diff, that is the volume preserving diffeomorphisms. And you know, it's just the flow you get by integrating the SD. Sorry, the OD associated with this velocity field. I want to be clear here. I'm denoting dependence here on the velocity field, and I'm going to refer to U bar as the entire velocity path in whatever space it's living in. So, in some sense, I want to think about, and this will tie into the picture we'll be discussing a little bit later. This thing is a function over top of. It's a function of the entire velocity path, let's say, in this case, up to time t. But in general, we're going to think of this as something that's like a random dynamical system. And I'll make that more precise in a second. But it's sort of like I have a flow that's over top of another dynamical system. In this case, the evolution of this velocity field. In which case, if I have some information about the long time behavior of this, I can often have some information, ergodic information about the long time behavior of this. It's much harder to get in a strictly deterministic setting, or at least a non-ergodic setting. Okay, so we'll also denote typically in some language, this is called the one-point motion. If I apply the diffeomorphism to one particle, xt will be the trajectory of that particular particle in flow. Now, the reason that this is useful in the first place is that I can solve the advection equation by characteristics. Okay, so of course I can always write my solution G as just, in some sense, the push forward of the initial data under this diffeomorphism. As so, note that because I'm volume preserving here, I don't really have to worry about determinants or anything like that. And so now, because I can relate behavior of G to behavior of this diffeomorphism, it's quite clear that if, for instance, I want to understand gradient growth, one of the things you can do is say, well, sure, if I take gradient of GT, and I'll do take its H1 norm, this is very clearly written up to some change of variables as the derivative of the flow. All right. This means inverse and transpose of this matrix or linear operator, let's say. If I'm on a manifold, this is with respect to the metric, let's say. This. And so in some sort of clean way, if we know, I mean, it's not exactly clean because we have gradient of G here, but if we know that the derivative of phi grows in some way, then that tells us that the gradient of G should grow. Okay, so gradient growth is kind of very closely tied to gradient growth or derivative growth of this diffeomorphism. So in particular, this motivates introducing the Lyapunov exponent associated, or the top Lyapunov exponent associated with this flow. So in particular, what I'm going to do is I'm going to linearize this flow, just as I did before, like this. So I'm going to denote d sub x here to be the derivative of phi at x on the manifold. In particular case, so this thing is just a map from the tangent space at x to the tangent space at xt. And then, so what I want to understand is that typically, okay, this thing may grow, but of particular interest is the asymptotic exponential growth rate in dynamics. So without sort of saying anything else about the flow, I'm going to define the top Lyapunov exponent, λ1, to be the asymptotic exponential growth rate of the norm of dx by t. Okay, so this is typically, I mean, the picture that you typically want to have in mind for this thing is that if I have two trajectories that are sort of infinitesimally close to each other, they are at least locally separating, like e to the λ1 t. So in particular, if λ1 is positive, you have divergence of trajectories. And so, in fact, when λ1 is bigger than 0 on a positive measure set, or let's say positive volume set of x, then we say there's Lagrangian chaos. Okay, so this is like what I'll take to be a definition of Lagrangian chaos. Of course, depending on who you talk to, they may have a different definition of exactly what they mean by a chaotic flow. But specifically here, we will say that if the linearization of the flow goes asymptotically exponentially like this, note that without any more assumptions, λ1 will depend on where you start. So in particular, you can have regions of the flow that are not growing exponentially. You can have regions that are very chaotic. If there's a positive volume region where you have a positive Lyapunov exponent, then you're saying there's Lagrangian chaos. Now, okay, so the first thing that having a positive Lyapunov exponent gives you, I'll just write it here, is that generally you can say something like this. There's some constant, depending some detail on, let's say, u bar and on x, such that I grow with λ1, at least if I correct it by epsilon. Okay, and this may not be true for every g, but you know, there's at least one initial g, such that I have exponential growth. So as long as it's positive, I can do this for any epsilon, and I will get gradient growth. Okay, so in general, if you're thinking, I mean, if the statement is in terms of like linear instability or something like that for this equation in HS or H1, in fact, you can do this for HS as well. But in H1, it says that if you have a positive Lyapunov exponent, then you grow exponentially in H1.
Here, does it matter if that x is like Eulerian or Lagrangian? Like, does x have to depend on t? Like, is it along some trajectory, or is it just a fixed?
Where in this up here?
Yeah, no, the dx.
It's the initial x, yeah.
It's just the initial x. It's not something else.
Yeah, it's not along the moving.
Does anything change if you make it along?
Well, yeah, okay. So if you linearize, I mean, in some sense, this is, so the equation, maybe it actually helps to write this way too, because the evolution of, if I take the time derivative of dx by t, it solves the linearized equation about this flow. So in some sense, this thing is evolving according to the linear phase portrait of u at time t along the trajectories. Is that what you were referring to, or do you mean if I?
Oh, I just meant the coordinate x. Is that something which is like Eulerian, or something which is also like, which evolves according to the flow?
So at least at the level of the manifold, it doesn't even make sense, I think, to take the derivative at a point which is not, you know, somehow the thing has to be mapping from the tangent space at x to the tangent space at xt. So I'm not sure. Yeah. Okay.
In the Lipschitz, you fix x.
Yeah, that's right. You fix an initial x. You're taking the derivative of that. Yeah. And then you take the, let me see. Yeah. I mean, if there were some other path on the manifold you were following, I'm not sure exactly what you would get. Okay, but this picture is actually important to point out because here, what it's telling you is that, and in fact, this kind of explains in some sense why proving positive Lyapunov exponent is extremely challenging thing to do in general. And it's because we have this picture where sort of I have this trajectory, which is going on, and I have sort of a linear phase portrait happening at every point, which is described by the gradient of u as t evolves. Now, I haven't told you very much about exactly how u evolves, but it could be becoming degenerate. It could be turning into sort of something that looks like a shear matrix. It could be hyperbolic, and then just moving all over the place. But then you're also following the trajectory of the flow. And so while the spectrum of this thing may be something you can easily study, in general, because it's moving around, the eigenspaces are flipping all over the place. And so, for people who are familiar with this is quite obvious, but sort of the whole essence of studying Lyapunov exponents is to understand how the eigenspaces are flipping around and to making sure they're not doing something that's going to destroy the exponential growth. So there's this sort of canonical picture in some sense of what can happen is that you could have this picture where most of the time linearly you look like a saddle like this. So that if I pick any vector that's not on the stable axis, everything sort of grows like this. But every so often you could suddenly turn into a rotation and flip me perfectly onto the stable axis, in which case I start to decay exponentially. Of course, that requires a lot of structure in the dynamics, but to rule out that structure is very challenging oftentimes. And so you really need to understand the precise nature of how the eigenspaces are moving around to really nail that down. All right. So what in particular does this give us? Well, I'm going to give you a general. So I'm going to work very loosely just for a second, but let's suppose now that my velocity path, I have this sort of infinite trajectory of velocity. What I can do is I can define a dynamical system on this path in the following way. It just takes u and it shifts it forward in time. Now, naturally, with this particular definition, it's not hard to show that phi t satisfies what's known as the cocycle property. So one thing that you see is that because we have this time-dependent velocity field, this flow is not a group per se, it's sort of inhomogeneous. But if you account for exactly what time the velocity field is, you can show, for instance, that if I shift the flows like this, if I shift the initial velocity, I can decompose the flow at time t plus s as a product of two, or a composition of two diffeomorphisms, where this one is just shifted the flow forward in time a little bit. And this property is very important. It's a cocycle property. And in particular, it implies that if I were to take its derivative and define it to be the following thing. So this is, I'm going to think of, I'm typically going to note the derivative of the flow by A here. And this is a mapping from, let's say, the path space of U across the manifold to something which is in SL2. In particular, it's, A, I want to think here as a mapping, or A at 10t is a mapping from the space of paths. I'm not going to be precise about exactly the regularity space the velocity fields are living in. can map into the space of determinant one matrices. And in particular, this.
If it were in 3 dimensions.
Sorry, SLD. Yeah. Thanks. Yeah, I'm often thinking in 2D here, but yeah, the 3D is also fine.
I think I got.
And this thing is often goes under the name as a linear cocycle. So this thing. So in dynamics, these things are studied very, very carefully with Lyapunov exponents. But the thing that I want to emphasize here is that there's a fundamental dynamical system that this is over top of that corresponds to, let's call this thing TT. Of these two things is going to be exactly what happens if I shift and then apply the flow. So something of this form is sometimes referred to as a skew product flow. However, here, without giving any more information, I haven't told you this dynamical system, it typically needs to have a little bit more, it needs to be ergodic for you to actually be able to say anything about it or to use it. I mean, it's not really true, but from the perspective of many of the tools that I'd like to use, in particular, the multiplicative ergodic theorem, and a little bit later, we'll see, and I think Elia will talk more about this, some of the rigidity theorems that we need for linear cocycles are very, they only really make sense when you talk about a linear cocycle over top of something that has a measure preserving transformation that's ergodic. So what I need to do is somehow put a probability measure. Let's call this PU on velocity paths. So here I'll write them as, let's say, at least continuous in time paths with values in some suitably regular subworld space. And I want it to be invariant in the sense that this sigma t is invariant under push forward of this shift and ergodic. Okay, so particularly, I mean, there's, let's say, many equivalent definitions of ergodic, but perhaps the cleanest one to use here is that if I have a function f, which is almost surely invariant with respect to sigma t. Actually, this means it's almost surely constant along the orbits of this dynamical system. And f is constant p almost surely. Okay, so in some sense, it explores the entire support of this measure. All right, so if we have something like this, which a priori, I should emphasize, it's not incredibly easy to construct this for general velocity paths. Okay, so this is one of the main reasons that we want to consider random velocity evolution. And of course, okay, you can do this, for instance, I mean, if you have a fixed velocity field, this is sort of trivially true. You can also do this for periodic motions and things like that. It's not terribly hard to do. And so in that case, some of the tools that I'm going to mention, particularly the multiplicative ergodic theorem, do apply. However, if you want to say a little bit more, particularly say something about the positive Lyapunov exponent, there's not enough there. At least, I mean, there might be, but I don't know how to do it.
Sorry, I didn't catch this. What exactly is a linear cocycle?
It's a mapping. So, yeah, it's like a mapping time t like this that satisfies the cocycle property again. So it's a linear mapping such that. But now with respect to this flow.
So it doesn't need to come from a derivative gradient.
It doesn't have to come from a derivative in general. So in fact, in dynamics, there are many papers written about just general linear cocycles over top of abstract measure preserving transformations or other sorts of dynamical systems, and they don't have to be derivative cocycles. But it is natural. In fact, I think the term cocycle comes specifically from the idea of having a diffeomorphism on a manifold, and then the linear map induces some mapping on the tangent bundle, and there is some cohomology connection that I don't really understand, but the name cocycle comes from that, because essentially the derivative mappings of any diffeomorphism have this property. Okay, so when we have these properties, this gives us a few things, and I'm not going to be extremely precise because I think some of this Elliot will be talking about again. Yeah, so in fact, all I'll mention is that in this particular setting, you have some tools at your disposal that are convenient. So the first thing you have is the MET, or in fact, I'm going to give a truncated version of it, sometimes known as the Furstenberg-Kasten theorem, which essentially just says that if let's say the integral positive part of the log of a x, the I have been a little sloppy stuff with the x. This is the volume measure on the manifold. If this is finite, then there exists a number lambda that's independent of any of the, it doesn't depend on the initial data or the entire velocity path. So there's, in some sense, there's a universal number such that it's realized as an exact limit.
What's an exact limit?
Instead of being a lim suit, so it's a limit. The limit is achieved and it's equal to this number. Now, without saying a little bit more, I mean, you can also put a condition on the integrability of the log of the inverse of this. And if you also do that, then one thing you immediately know is that lambda has to be finite. Although the way I've stated here, a priori lambda could be minus infinity, because the spectrum can kind of collapse. This thing could be very degenerate. Okay. So this is one important tool that we want to use. But apart from that, we need a lot more structure in order to say that we have a positive Lyapunov exponent. And then to say further questions, for instance, things about mixing, we need even more. So let me give you some examples. Of which there are not terribly many. Although Weissang might have plenty.
I was actually going to ask you that your base of your stew product flow is both the U and the phi. It's not the flow in U, it's both U and phi.
It's both U and phi for the linear cocycle, yeah.
Okay, then P is just any. You're talking.
These, I'm just guessing. Right now, I'm saying, suppose I can find an ergodic measure for this shift dynamical system. I don't know exactly what it is at the moment. Our goal will be to construct one. Yeah. Right.
So
yeah.
Right. A without the superscript is just 1.
Oh yeah. Yeah, that's right. Okay, so I'll just give you an example. So particularly if I'm dealing with continuous time and flows like this, there are not that many great examples. So for instance, I can take, I have to pick the manifold carefully, but for instance, I can take it to be the diffeomorphism generated by a velocity field where this thing is say an anisot diffeomorphism. or an Amosov velocity field. So this would be like the vector field associated with the geodesic flow on some negatively curved manifold. And okay, the manifold here would be like the unit cotangent bundle for the negative curve system. This is an example of a uniformly hyperbolic flow. Without getting into exact details of uniform hyperbolicity, what it really just means is that the derivative of this flow has a nice splitting on the tangent space into a stable and an unstable thing. And this is uniform over everywhere on the manifold. So in particular, it gives you this beautiful foliation of the manifold, the stable and unstable manifolds. And in particular, these things are constructed almost to have positive Lyapunov exponents. So this thing. Now, this is very special to being in dimension bigger than 2. If I give you a velocity field which is not time dependent and you're dimension 2 and it's smooth, you can't have a positive Lyapunov exponent. And that is just because of, what's the theorem called? It's the characterization of the omega limits at 2D. Poincare index, yes. Okay, but so there might be other flows. I mean, there's a lot of numerical evidence. I can give you tons of very specific fixed in time velocity fields in 3D, and there's a lot of beautiful pictures that suggest there's a positive measure set where you have a positive Lyapunov exponent. But actually proving that, it seems to be a bit out of the reach, except for very specific examples. And for general time dependent motions. It's not immediately clear how to do it. But okay, now with that in mind, if you add noise to the system, there's a ton of work on proving positive Lyapunov exponents. So this is mainly what I'm going to talk about. So what I'm going to do right now, without giving you the exact technical details, is sort of loosely state the theorem. And that is basically there exists a large class of velocities in sorry. Continuous in time. Take values in H sigma. I think we, for technical reasons, need sigma bigger than 3. So the thing you should have in mind here is that this is me. I'm putting a probability measure on the space of paths, and this probability measure is, for instance, supported on solutions of forced Navier-Stokes equations in, let's say, 2 dimensions. Okay, but in fact, the point that I want to make here is that with this class, lambda 1, which is equal to limit as t goes to infinity, 1 over t log is positive, and this is p cross the lane, almost sure. So this means that for almost any velocity field that I sample out of this measure, I will have a positive Lyapunov exponent. So in particular, if I am, and I will describe the model in a second, if I am considering the stochastic Navier-Stokes equations with white and time random forcing, it means that there's for almost every realization of the noise, there's a particular solution to Navier-Stokes, and that thing will have a positive Lyapunov exponent. So in particular, there's a huge number of paths that are solving Navier-Stokes that are giving you this property. Okay, so it's not like an average thing or anything like that. So in particular, like the video I showed you, is kind of a realization of that. So. I hope this is not too vague. I will try to. The problem with stochastic PD is it can get very technical, and I would like to, let's say, not make it as technical as it can be. Okay, so before I describe the models, I want to actually go a little bit further and talk about mixing, in particular exponential mixing. Let me remind you that I think next week Elliot will be talking a bit more about the details of this theorem, and particularly, so we use some sort of we prove a rigidity criterion on sort of group action on projective space, which is something that's very very important, but also in particularly hard to do in infinite dimensions. And anyway, so Elliot will talk about that. So I will save some of that for him. Okay, so exponential mixing, the way I had sort of given it before from a PD perspective, we would say that the velocity field here is exponentially mixing if in some negative Sobolev norm I'll pick h-1, that there's some rate like this, such that this thing decays like this, and I'm assuming for now that g is mean 0. So the initial g is mean 0. Sorry, that should be up to a constant. Okay, so we say it's exponential mixing if there's some positive gamma like this, such that I have exponential decay in h-1, as long as I pick initial data which is suitably regular. Now there's a natural sort of dynamical systems, particularly let's say within smooth ergodic theory. That typically comes up, which is actually equivalent to this version of mixing, which is suppose let me just define for a second. If I give you two mean 0, they don't have to be mean 0. Let me give you two functions f and g, which are let's say L2 or something like that, and we define their covariance as the integral of fg minus treating these things as random variables on the manifold with respect to Lebesgue measure. Then we say we have exponential mixing. There are more general ways to formulate this, but the covariance between f along the orbits of phi and g, they decay like e to the minus gamma t times some norms of f and g, which it's quite important to mention that these are regularity norms. And in general, if I'm picking the same space, particularly in the setting I'm talking about, it doesn't matter what norms you pick. They could be something like CR, they could be HS for NES positive. As long as they're measuring some form of regularity. In fact, you can often get even more precise statements if you use anisotropic Sobolev norms that line up with the irregular along the unstable manifold and irregular along the stable manifold. But in general, we say something like this. And it's important to recognize that this is equivalent to h-1 decay, more or less, if I take these norms to be the h1 norms, just by duality. Okay, so this is equivalent. All right, just because, of course, I can always write g h-1 is the soup of f h1 equal to 1, integral of f equal to 0, of the integral of f times g. Yes, or the covariance. All right, so exponential decay, this is the same. Now, if we go back to the example that I mentioned about a diffeomorphism, which is this Anosov flow, this is also exponentially mixing. So this is another sort of very clean, uniformly hyperbolic setting where we have exponential mixing. Okay, but more generally, there's actually been quite a lot of work in the PD community trying to study mixing. And here, I'm only going to restrict myself to the case of smooth or at least Lipschitz velocity fields. There's been even more work in the case of rough velocity fields, in which case it's not so easy, or you can't do it, but talking about the flow is something that's much better to do. But in the case of smooth velocity fields, there's a ton of work where people can show that they're exponentially mixing. You can construct velocity fields which are exponentially mixing. So, for instance, the work by Alberti, Mascala. They're able to construct a time-dependent velocity field, which is Lipschitz that mixes. But in general, it's very hard to construct these things by hand that are not, again, in a uniformly hyperbolic setting. Okay. However,
so what was the setting they did this, Alberti and all?
Right. They constructed, so they essentially showed, I think, I may not have it fully right. I think they showed that you have something which is at least L infinity in time, Lipschitz in space, that is exponentially mixing as a velocity field.
So there exists one.
There exists one. They build it in this they build it sort of using, I think, the piano curves.
Not stochastic or?
No, it's an explicit construction, yeah. Right. Are we breaking at 3? Okay. Yeah.
Make it 3 and
then come back at 30 minutes.
Okay.
So I'll mention, say, the pseudo theorem again. There exists a large class, although potentially not as big as this class, which is interesting to mention, but there exists a large class of random velocity fields. For instance, supported on 2D stochastic Navier-Stokes, which is an example such that we have exponential mixing. But I want to be extra clear about that, because this might be referred to in some sense as a quenched mixing or quenched correlation decay. So there in particular, I'm going to make it explicit. There is a constant which is random or depends on the entire. And in fact, the way it's constructed depends on the entire future of this of the velocity path. So somehow it's like you have to see everything the velocity field's doing. You get this prefactor, which can account for tons of transient growth. It could be quite big, but eventually you get exponential decay with this rate. And these norms are, let's say, H1. They can be anything. Okay. So just to mark this gamma as possible. All right, so in the same setting, in the same random setting, we can show this. And so this is something that I'll talk about 2 weeks from now, with the more details on how to construct these. It's actually kind of complicated, so giving all the details would be quite challenging right now. But let me give you the third part. Perhaps maybe one of the more interesting ones, because it's at least in dynamics, there's not that much of an analog of this, or at least in terms of people studying it. And that is now, what happens if I add diffusion? Okay, so I want to study the advection equation with diffusion. Now, in the PD community, people know that this is actually quite a challenging problem. So I have this advection-diffusion equation. I add this perturbation, which in some sense is a singular perturbation of the equation, but it's also smoothing everything out. The interaction between the advection and the Laplacian term can be pretty complicated. So in particular, this is trying to generate lots of high frequencies all over the place. In particular, it's mixing. The Laplacian acts even stronger and stronger at high frequencies, so it starts to eat everything up. As a result, you'll get a lot of, you'll for instance get decay of this equation, which is way faster than you would for the heat equation, because there's this conveyor belt of pumping everything to high frequencies. So understanding exactly how much of an improvement you get is in fact quite a large, say that there's a large number of people interested in that in the PD community. So let me just give you sort of a general take on this. So if I take this equation, for what I mentioned, particularly in the case if I have a smooth manifold and let's say with or a compact manifold without boundary, then just by brutal energy estimates, right? Very easy to show, sorry, negative, that this equation is true with some positive constant and kappa being this. So that there is a natural diffusive timescale in which you expect to see decay of this thing by a factor of, let's say, 1/2 or something like that. So in particular, it's natural to say that, okay, let me define ST to be the solution operator. So this particular GT is equal to STU G0. Then it's quite natural to say, all right, so there's a time scale in which I expect to see order 1 change on this equation. Let me define TK to be the first time in which I see ST decay by like a factor of 1/2 or something. Okay. Then what this is saying is that TK is at least less than 1/kappa. Okay. I know my cases. Luckily, I don't have any other Ks anywhere. Not always the case. Okay, so if I wait at least time 1/kappa, I will see like I'll see a decay by 1/2. But generally, like I mentioned, it's usually much faster than that. So there's been quite a lot of work on this, but so in particular, there's, okay, I need to actually get the long list of authors here.
So exact inequalities, there's no constant.
Oh, sorry, no, there's a constant. In this case, it's, let's say, the largest eigenvalue of the Laplacian. But generally, there's some huge constant. So in fact, this kind of stuff was Konstantin Kiselev and Richard Zlatos. They didn't formulate it exactly this way. But they essentially studied this problem from the perspective of, if I have a velocity field which is mixing, do I get any enhancement of the decay rate? And they call this dissipation enhancement. But since then, there's been some work, so particularly by Michele, Cottizolatti, Mattias Dogadino, Tarek, where they gave more precise characterization. They said if I have a velocity field which is exponentially mixing, then I can actually get a quantitative upper bound on this dissipation time in terms of kappa. And I will write what it is in a second. And there's also related work. You get the same estimate, at least in the exponentially mixing case by Gartemeyer and one thing. And in particular, what they show, at least these two works, is that if U is exponentially mixing, then T kappa is less than or equal to log kappa squared. Now, this in particular tells you first there's a major speed up compared to the heat equation. So I only have to wait log kappa time instead of 1 over kappa time before I start to see the equation decay away. But the interesting thing, or at least let's say the frustrating thing about these estimates, they're quite explicit, but they're not optimal. So one thing that you can show, just check the time. I'll mention this and then we can break. One quite easy thing that you can show is in the case of a Lipschitz velocity field on a bounded domain, U is Lipschitz, and whatever time dependent as well, but L infinity in time. Then you have an let's say on compact. Then you have a double exponential lower bound in L2, which can be more or less written something like this: e to the minus kappa. Let's say there's some constant here that depends on the velocity field. E to the gamma t. Okay, and it's already interesting to mention that there's no known proof that you can do better than this, although it's expected to be true generically, showing that you can't decay double exponentially fast is still open, as far as I know. But if you look at the time scale, the dissipation time scale on this thing, it takes log kappa time before you see an order 1 growth. Because all you're asking, let's say I want to wait until I see this factor go less than 1/2. That just means I need to wait until I see kappa times e to the gamma t less than a particular number. So for this, it actually tells you that the dissipation time is bigger than or equal to log kappa. Okay. And I think maybe we'll break in a second. So what I'll tell you, I think when we return, I'll mention that, so in the case of these general random velocity fields, we can recover the optimal time scale. We get an enhanced dissipation, but in fact, we get a much stronger thing, which I'll call uniform in dissipation mixing. And in some sense, I'll try to give you a point that this is maybe the right property to study and the one that should be holding true more generally than just dissipation enhancement. Okay, yeah, I think that's a good breaking point.
Questions? So that gamma is the same gamma as the mixing.
It probably is, but let's say I'm not too confident about that. Yeah.
And I missed this, but is there a relationship between gamma and lambda 1? No.
Not easily. So if you read a physics book, they'd say that they're the same.
I see.
They're definitely not the same. I'll try to make it clear at some point, but there is an aspect that they're related, but already it's more closely related to what's known as a moment Lyapunov exponent, which is sort of an average Lyapunov exponent related to large deviations. But even then, there's not an explicit relation to that because the decay rates there's some irreducibility factor you have to take into account that destroys the connection.
So the method of proof as well for these two theorems are different.
The method of proof is quite different for this. Yeah, I mean, one relies on the other. So I'll say that being able to get mixing, I use very strongly the fact that there's a positive Lyapunov exponent. And then once you have that, you can get exponential mix.
So does this mean I can replace the kappa there by log kappa in for all time?
Yeah, so roughly it means that if I wait long enough.
Does it technically mean that? I'm not quite.
Yeah, it means that I can do that if I wait long enough, or at least if I take t big and log kappa, I see exponential k looks like this.
For all time.
For all time, yeah. All time big enough.
So you mentioned stochastic Navier-Stokes a couple of times.
Yeah.
Is this still true if I just take the linear stochastic heat equation, so I expect the value and making sure that's difference free and whatever?
Yeah.
Does it become easier?
Yes. It does, yeah, much easier. So, I don't want to give the impression that this is a feature of Navier-Stokes. It's more of a feature of suitably generic fluid motion. I will hope, if I have time, I'll try to give you the condition. There's a very clean condition on how generic the velocity fields have to be. They need to span a set of modes and their linearizations. But
It's a feature of random divergence B vector field. Is
yeah,
dependent.
pretty much. Although it's frustrating, it's not so easy to formulate. I mean, there probably is one, but it's quite hard to give a general statement. It's like all things in this one class. Like, so we proved for examples because there probably is a way to do it, but I don't know if this is a very clean way to do it. So it is possible you could write a theorem that says, here's a velocity field that has this huge list of conditions. It has all these properties. But yeah, that example is a very clean one to give. I will write it hopefully if I can squeeze it in and after the break.
Okay, so I guess we can enjoy our tea for 20 minutes and then leave.
Do you know this old work of Ruel's where he looks at all the way out from maybe go or so. For any of that stuff, I mean, I'm just trying to remember about it because if you're looking at just the top exponent,
Yeah.
he's looking at all the exponents for some reason and trying to relate it to some problems in fluids, but I can't remember what he does.
Right.
I'd have to look it up.
It is possible to consider other exponents, like the full Lyapunov spectrum.
Yeah, that's what he was doing, I think.
But let's say for the cases we're only in dimensions 2 or 3.
Yeah.
In dimension 2.
3 dimensions is what you want to look at anyhow.
Yeah, exactly.
I mean,
So
that's not a drawback.
in 2D, there's no point in looking at the other exponent because it's all volume perturbed. So the other one's just equal and negative sign.
But he's not doing passive, he's not doing induction by scale.
He's looking at high dimensional dynamics. Yeah. So that is a different question, but it's also very interesting, I think, to study the full Lyapunov spectrum of like a very high dimensional dynamical system.
And there are all kinds of conjectures about how they're distributed and that kind of thing.
Yeah, that's a very hard question to answer. There are things you can say about, again, within the random setting, you can give sort of very general conditions on when you have simplicity of the spectrum that are all separate from each other. But it's incredibly hard to do that.
Yeah, no,
Yeah.
familiar with that problem.
Yeah. No, I don't know. There are related questions for Eulerian, the Lyapunov exponents for the Navier-Stokes or something like that in itself.
Yeah, I have to look up what he did.
Actually, what can you say about the Lyapunov exponent for the scalar?
I'll talk about that in a second. Yeah. By Euler, I meant for the
I
velocity
know,
field.
yeah, but there's also there.
Never. Sure.
Whatever you want.
Oh, okay. All right. Yeah, I wasn't sure if we
No,
were
sure.
waiting for time.
No.
Okay, so where I left off, I was talking about the effect between the mixing properties of advection and the Laplacian, and how you can get sort of an enhancement in the L2 dissipation. And I mentioned that in fact, this property, particularly in the case when you get the optimal dissipation timescale enhancement, which would be a log kappa timescale, is a consequence of, let's say, a stronger property. So in fact, we say that we have uniform and kappa mixing if, I'll write it for the PD. If for the advection-diffusion equation, we have something like this. Oh, sorry, H minus 1. If you have exponential decay like this, where gamma is independent of epsilon. Sorry, of kappa. Okay, now, of course, this is maybe not something that's that easy to show, but let me at least convince you first that if you have uniform and kappa mixing, then you immediately have enhancement, dissipation enhancement on this time scale. Because it's not actually that hard to show, but it's a nice little calculation that's actually doable on the board. So let's take first, if we take the advection-diffusion equation, it's quite easy to get an energy estimate in this form. Okay, sort of the standard squares. And so because I have H minus 1 decay, which is uniform in kappa, all I'm going to do is just interpolate this. So this is an H1 norm. I'm just going to interpolate it between H1 and H minus 1. So this thing is greater than or equal to, sorry, not FG. Sorry. Okay. And so now what we see is that, so this thing is decaying exponentially in a way that's uniform in kappa. But if we,
Wait, the inequality.
did I do it wrong?
I think you want the next equal.
Oh, yes, you're right.
Because you have the minus.
Yeah, thank you. Very strong lower bound. And if I do this, then it's not hard to show. If I divide through by the L2 number, you can get a differential inequality, GT, on 1 over the L2 number. In this case, now it's the inequality. It's this direction. Okay. And if I do this right, then of course I can bound this below even further by kappa divided by, say, c squared e to the minus 2 gamma t times . Okay, and now I just want to integrate this thing and then solve for g and L2. And if you do that, it's quite easy to see. I mean, I'm integrating this exponential. If I flip everything and estimate it, you can see that this thing is bounded at least up to some constant by kappa times 1 over. Get that wrong. I did one cheap step, I think. Because you might get a different power of kappa, I think. Or no, this is right. So one thing you say, I have an H1 norm on here instead of an L2. That's not a huge deal when you're dealing with the advection equation. So this would really be like L2. I think you get something L2 times G0 and H1. Of course, because it's parabolic equations for regularizing, I can just take the initial data down to like time 1 and then iterate again, and I'll pick up an inverse power of kappa, which will just increase this power a little bit more. So it'd be like power of 2 or something, or some fractional power of kappa. The point is that I get this estimate like this. Now I just want to see on what time scale does this decay by an order of some factor, and immediately see that if I wait for t less than something that's like log kappa up to a constant, then I will have decreased by some constant factor. So the point I want to make here is that if you have uniform and kappa mixing, it immediately tells you that you have a uniform L2 exponential decay with a prefactor that's kappa dependent, but you get the same exponential rate. And this gives the following interpretation. Of course, I mean, because the L2 norm is also essentially preserved or decaying by the equation, it doesn't mean this thing blows up in kappa. I can also bound this thing by the min of 1 in this factor just immediately. But what it does suggest is if I look instead at the following thing, so these are sort of the scalar Lyapunov, the scalar top Lyapunov exponent. So for instance, let me define negative gamma kappa to be equal to the limit of t goes to infinity 1 over t log of the norm of the solution operator L2. In fact, one thing you can show, I think I mentioned this already or hinted at it, this thing doesn't depend on the norm. So in fact, I could take HS and this number will be the same. In particular, if I have a velocity field which is ergodic, it's definitely true. And this is, the thing about this is an infinite dimensional Lyapunov exponent. This is a compact operator. So it's more or less determined on a finite dimensional space. And in particular, the Lyapunov exponent is determined explicitly on finite dimensional space. So that there's this general idea in Lyapunov exponents that they should not depend on the metric that you're measuring in. And this is very much true. If you measure them on manifolds, it doesn't matter what metric you have. It doesn't matter what norm you're using. They're all equivalent. And that the intuition is that sure, changing the norm will give you a prefactor, but when you take the log, it'll all vanish under changing log, asymptotic logs. So this thing doesn't depend on the norm I'm measuring it. So it gives you this picture that if you wait long enough for the advection-diffusion equation, you'll always see the same rate, like this. But in particular, it's also telling you that if you have uniform and kappa mixing, that gamma kappa is bounded below by some number gamma, which is potentially strictly positive. So what this is telling you is that there's this asymptotic rate which is behaving singularly in kappa in this mixing case. So as you try to send kappa to 0, it's approaching some fixed number which is bounded away from 0. And this is for instance not necessarily the case. If I give you a flow which was like completely integrable or had lots of just only clean shearing, this thing will typically converge to 0 polynomially or at some power law of kappa. But here, so I would sort of say that this is sort of a signature of uniform and kappa mixing. Now, I did say that this kind of
It doesn't imply it, does it?
no, I don't think so. Yeah. Although, you know, maybe it suggests redefining it.
What was the question?
No, what do you mean it doesn't apply? But
It doesn't apply it in this strict sense, only because first off, there could be prefactors that are.
Okay, it doesn't apply, meaning gamma bar is not gamma.
No, there could be secular terms. For instance, I mean, it's a slightly more general. Like this thing could have polynomial prefactors.
Okay,
Yeah. So this would imply something similar with like a slightly different. Oh, okay. Yeah, you're right. Actually, if I change the power of gamma, yeah.
you change the power.
No, you're right, you're
I
right.
don't understand.
It's okay.
You're right. It's okay. Yeah. Never mind. That's true. If
I
you
think
do it for
Font
different.
is perplexed, saying that this cannot possibly be true. Did I understand you?
No.
No,
My
he's
question
right.
was, I know situations in which you have positive Lyapunov exponent, but you don't have, real mixing, so.
Yeah, this is
Mixing is a stronger condition now.
that is generally true. But this is the Lyapunov exponent for the scalar equation.
For the scalar equation, though.
So when the scalar equation is decaying in a way that is uniform in kappa, then it's this is uniform kappa mixing. So I'd say that this is sort of like a characteristic of this. Now, I want to mention that I've said that this isn't necessarily been studied in the dynamics literature, but there is a very nice work by Dyatlov and Zworsky that essentially proves something like this for Anisov flows again. So we'll go back to my favorite example. So first off, if I give you an Anisov flow like this, one thing that's very nice is that if you look at the resolvent of this, so here I'm treating the vector field as a differential operator. So take a look at the resolvent of this. If I normally just think of it as on L2 to L2, the idea here is that I can construct, so particularly because it's in a uniform hyperbolic setting, I can construct Sobolev spaces. They're anisotropic Sobolev spaces. So call them I'll just call them HX or HV. Okay, which are in some sense, they require regularity along the unstable directions, and in fact are distribution valued. They're measuring negative regularity in the stable directions. And if you extend the operator to these spaces, in fact, this thing becomes a Fredholm operator. Okay, and in particular, it has a very clear spectrum that are all negative, or they're all on the negative, the real part. So let's say the spectrum of this resolvent when extended to these spaces as negative real part. And these things typically have a name. They go by Rouel-Polycott resonances. So they are sort of a feature of the extreme mixing uniform hyperbolicity of this system. It means that in some sense I can build spaces that very explicitly take into account the stable unstable foliation on the space. The second I have that, this operator turns into has really nice spectral properties. But moreover, Dyatlov and Zworsky showed that if I actually take this equation and I regularize it with Lipschitz, that the spectrum of this I did that correct. Let me state this slightly differently. Let me call these the poles. So it's from the result. The spectrum, however, of this guy converges to these Rouel-Polycott resonances as kappa goes to 0. So in particular, the top one, which is this guy, converges to a number which is strictly away from 0 and is like this. So this is kind of a feature of very chaotic, very mixing systems. And I would conjecture that it's something that you expect to be true for many systems. Of course, the proof of this is extremely challenging to do. So it's not necessarily easy to get.
So you're saying you cannot do, or can you prove this for
This-
like a random, that one for a random?
I can't even prove that they converge. So they prove that these things are they're continuous in kappa as you send kappa to 0, and they all converge nicely to certain numbers. The best I can say here is that this number is bounded below by a number that is away from.
Yeah, okay, so that one you can say.
Yes, that I can say. So this comes from uniform kappa mixing, but in general, I expect this picture to also hold. So that there's a whole family of Lyapunov exponents for this thing, and I think that they should all converge. And in fact, they should be continuous in kappa. Is my guess, but again, as maybe people in dynamics know.
The real part of the pole for this part.
Oh no! I'm trying to modify my statements on the fly. The poles of this resolvent,
Yes.
when augmented on the space, so there's a meromorphic continuation of this function.
Yes.
These poles, the spectrum of this converge to these poles. Okay. So I mean, in some sense, you want to think about the Ruel-Polycott resonances as the spectrum of this advection operator. But you just have to pick the right Sobolev space for that to have a nice spectrum. Because I mean, as we know in general, if I look at that on L2, it's all just absolutely continuous spectrum on the imaginary axis. Okay, so the final pseudo theorem I'll mention is that again for a large class, but this one's actually subtle, right? Of random velocities. In fact, it is the exact same class of random velocities that we get exponential mixing for. The following holds. There exists a positive and a constant, which is kappa dependent, but in random, but has the property that its moments are bounded uniformly in kappa. There's some function u at time 0 that doesn't depend on kappa.
Depends on P.
Depends on p. There's a constant here. Yeah, thanks. And I have decay h-1 like this up to this kappa dependent random constant. So this is telling you that you pretty much have uniform and kappa mixing, up to the fact that there's a constant here that is almost in L infinity of omega, but just barely misses. So it's an LP for every P, but not L infinity. So it could have some growth. But in particular, this does imply that for every delta greater than 0, that you do have uniform and kappa mixing. With probability bigger than 1 minus delta. Okay, so that you can always find a really small probability set where if I look away from it, then I have uniform mixing. Okay, so in particular, this still implies that there's an enormous number of paths, enormous number of solutions that solve it, just not almost every one. It's slightly subtle, but in fact, it also still implies this fact. Because this d kappa, because of the fact that it has bounded moments, when you take limits like that, there you can use ergodic theory to show that everything gets bounded by its averages, which are uniformly bounded in kappa. So this is still true. So this is sort of a setting in the random setting where this does not necessarily imply this explicitly, because you can have constants that depend on kappa, which technically breaks the uniform kappa mixing directly. Is that clear? All right. Okay, so let me, in the remaining time, what I'll do, I'm going to state some of the models to give you an explicit sense of what it is we're actually looking at. Also, maybe to help Ellie out, because to give him a little bit of preliminary material before he works. And then I'll try to just give you a very rough idea of some of the tools used to prove these things. But just remember, next week we will be explaining in a lot more detail how to prove Lagrangian chaos. And then after that, we'll explain how to prove mixing. But there are a lot of tools we need. So let me start with the fluid models. So specifically, I'm going to start for now with stochastic Navier-Stokes equations on T2, although we can consider a lot of other models. So let me just first write this one down. So I want to consider the evolution equation for divergence-free velocity field. Of the following form. Okay, so for those of you who are not familiar with stochastic PD, which I think it's maybe I'll make that assumption. This equation is Navier-Stokes with a forcing that's this random sum of Wiener processes. So here, WKT, they're IID Wiener processes. They're canonical Wiener processes. EK are a basis, let's say particularly the Stokes eigenfunctions for divergence-free test functions. Let's say L2 div. And these sigma k's are a series of weights, which we're going to assume have some ability criterion. In particular, when they decay at a certain rate and have the right decay, this thing will take values in a particular Sobolev space. And so it'll give me a forcing that's regular.
So those are fixed constants.
So those are just fixed sequence of numbers. Yeah. So sigma, let's say sigma k here, we'll think of as just belonging to elements of little L2. Now, the thing I want to mention is that this is basic for stochastic PD.
You're not assuming that you're assuming it's white in time or not?
Yeah, these are white and time. Yeah, sorry, the dot here. So I have to indicate that. I'll explain what I mean by solution in just a second, actually. So the types of solutions, when I say what I mean by solution, I'm going to consider mild solutions. Because in fact, I find these significantly easier to think about. From a PD perspective, you're very used to thinking about subcritical semi-linear SPD. This is definitely the natural approach to use because you can use pretty much all the same tools. So I want to think about a solution. Looks like this. This piece of the ray projector. And then the noise ends up taking the following form. As you might expect, except here, I'll write it sorry, like this. Okay, so I act the heat semigroup on this basis function, and then I just integrate this as a stochastic integral. Sorry, with respect to each one of these. So this thing has a name. It's actually referred to as stochastic convolution. And in fact, there's a huge number. Yeah.
The sigma k's are all positive. Am I correct?
They don't have to be,
Don't have to.
but I will assume that. Yeah, assume they're positive. The thing is, up to a, because the Brownian motions are changing sign, it doesn't really matter. But up to a change in law.
No, but I mean, they're not
Yeah.
zero. I mean, you're definitely like, infinite dimensional in this perturbation. You're not going like to be concentrated on like, say, finitely many nodes.
Yeah, exactly.
That's what I meant.
No, that'll be an assumption, yeah, and that's a very crucial one that I haven't really emphasized very much. If you are familiar with the work of like Heyer and Mattingly, for instance, where if I can just take a few modes of this,
Yeah.
Solutions are even easier to make sense of in that sense because it's a really low
Yeah.
dimensional forcing. But the bigger question is whether you have ergodic stationary measures for this. If I force all the modes, solutions are a little bit harder to make sense of because you
Yeah.
have so much noise. But as long as the noise is tame enough, getting a unique stationary measure is a lot easier. And in fact, it's kind of like I've turned this equation at the level of probability measures induces an infinite dimensional Kolmogorov equation. And in some sense, when I force all the modes, it turns it into an elliptic, nice elliptic equation, and I get a full, there's a sense in which I can make very precise that it is regularizing. And when you have hypoelliptic infinite dimensional things, the infinite dimensional regularity theory just doesn't exist. So there's no in between. And that's very crucial for what we need. For those of you who are not super comfortable with stochastic integrals, it's very easy in this particular setting to just treat this as a derivative. You can integrate by parts onto this thing and write everything as an explicit function of just the Brownian motion as a path. So you don't even need to take stochastic integral per se. Okay, and so actually, in fact, doing that, we can get the following theorem. So I'm just going to state the general well-posedness theorem because I guess we have to do that. It's more or less classical. So you can find if you do want to learn a little bit more about 2D stochastic Navier-Stokes, Cookson and Shuriken have a fantastic book on mathematics of 2D turbulence. It's called, the name is perhaps a bit misnomer because there's not anything about turbulence in there. But it has everything you may ever want to know about 2D stochastic Navier-Stokes. And the theorem goes like this. So of course there's many well-posedness results, but in the one that I'm interested in here is assume that the sigma k's are bounded like this. Or alpha bigger than some number 5. It's a little ugly, but then for each U0 and H sigma, or sigma is an alpha minus 2 and alpha between alpha minus 1, then there exists a unique mouth solution. So in particular, it solves this equation almost surely with respect to some probability measure on the noise. And this solution belongs to LP of the probability space. And it has continuous paths, but not much better than that. I mean, you can get Holder in time with values in H sigma. Okay. I mean, you can be a bit more precise. Like it's, you can get better regularity in time if you pay space as usual for Navier-Stokes. But the more important piece here is that there also exists an RDS, a random dynamical system. This is crucial. And in fact, it's not trivial to prove at all. So I mean, even in general, there was an enormous amount of work done just proving that a random dynamical system exists for a stochastic differential equation. In infinite dimensions, it takes work to show. So let me say what I mean by an RDS. So in particular, I mean, the solution can be written up as a flow map of the solution, where there's some noise parameter. So it's very similar to the Lagrangian flow I consider, but there's some noise here where I think of omega as belonging, let's say, to the space of one-sided Brownian paths, taking, or let's actually just make it a little bit, and products of that space. Okay. And in particular, I'm going to put a probability measure on this space, which is just and products, or let's say infinite many products of the 1D Wiener measure, or the Wiener measure on the one-dimensional Brownian motion. In particular, this is a Gaussian measure on just continuous paths on one side. Well, I actually meant, sorry, these are 0 and 0. And moreover, there's also a dynamical system on these paths, which is very similar to what I described before. It's a shift operator. It's known as the Wiener shift. And if I take one of these omegas in omega, then the shift is omega t plus s. Okay, so it just shifts it forward. It's very easy to see that this, because this is the Wiener measure is invariant under shifts forward in time like this, and this p is ergodic. Okay, so put another way, omega with its natural sigma algebra, this p, and this theta t bigger than 0. This is what's known as a measure preserving transformation, or measure preserving flow, let's say. This is essentially one of the fundamental building blocks of dynamical systems, at least measure theory of dynamical systems. And having that in play, an RDS is essentially this map here, phi t, is a map from omega across h sigma to h sigma, which is measurable. Okay. I'm going to assume it's also continuous in the h sigma variable, and it satisfies the cocycle property that very crucially holds for every omega. I know that sounds like a technicality, but it is very, very important when lifting these things to skew product flows, which again, we'll see that Elliot is kind of a very, very crucial ingredient for being able to say anything about Lagrangian cast. So this is the cocycle property that holds for every omega. So not just almost every or something. Now, under these conditions that we have here, essentially, sorry,
The philosophy behind it. I mean, what does allow you to actually have a statement valid for all omega, although everything so far was probabilistic? I mean, it sounds kind of cheating, no?
Yeah, I mean, it shows that like there exists a map that you can kind of fill the holes in. So that sort of with any general solution for an SD, if I can get pathwise solutions, I can construct what's known as a crude cocycle, which is one that satisfies for almost every omega. The question is the probability spaces can potentially change depending on time. So you want to find one that works for all time, and then you can just define it to be whatever you want off of that, as long as it satisfies this very trivially. So it's more about finding, it's like a kind of technical matter, but it's not an easy construction to do for Navier-Stokes, but you're trying to find a set of measure zero things that are sort of uniform.
They're sort of preserved by the, like that is not happening actually, that you kind of flow and end up for a set of positive measure into this measure zero set that you excluded. Is that kind of the technical issue?
Yeah, I mean, something like that, right? It's basically, in the sense that I have this map, which is defined for every omega, I can easily extend it to being defined for almost every omega. If I have this thing being, sorry, if it was defined for almost every omega, I can easily extend this because of continuity to be defined for every omega. For this thing, because we have continuity of time, but we have also this other space. There's a challenging measurability problem with the fact that if I have this defined for almost every omega, yeah, the sets that are defined but can potentially change for each one, and I have sort of uncountable unions for each one. So I don't really know of a great example of a cocycle that's non-perfectible, I guess. It's just that
So it's a matter of, because you have two variables.
it's a matter
It's
because
more
you have
like
two
for
variables.
meaning, essentially. You don't want to
Yeah.
give up a set of measure zero on.
Exactly.
You want to give up a set of measure zero kind of uniformly in all omega, for instance,
Yeah.
not that it depends on the omega, something like that.
That's the idea. Yeah. I mean, it's a. I don't mean to make it into something which is a super important feature, although it is very often overlooked feature of constructing random dynamical systems. People for a long time didn't actually know how to do it. So there are technical aspects to getting it to work, but I'm going to assume that. I'm just going to take advantage of the theorems that have already been proven. And once we have that, okay, why don't I wrap up the statement I want to make. So let me give you the condition here. Under that condition on the noise, there's one more thing you get, and that is the kind of stationary measure, unique stationary measure. So in particular, under those conditions on the theorem, there also exists a unique probability measure, some H sigma, which is stationary, and I'm going to write it in this sense with respect to this random dynamical system, which means that if I push forward this measure under this map and then average over all the omegas, that it comes out to be the same. So it's saying that if I flow dynamically, if I flow something that started with this probability measure, on average, I get the same statistics at every time. Or this for every t. Okay, so you can write this again in terms of Markov kernels, which is something that we'll have to do a little bit later. But this having a unique stationary measure is crucial because it implies that the dynamical system, this random dynamical system, actually has ergodic properties. So in particular, it implies that if I take 1 over t of some function, I mean, there's more general versions of this, of the solution of Navier-Stokes like this, that it converges as t goes to infinity to the integral of f of u. Moreover, this picture here is a very, very clean way of seeing the Markov property for Navier-Stokes. Because what we see here with this map, this solution only depends on omega between 0 and the time of evaluating t plus s. This one, when I shift the path, depends on omega between s and t. And this one depends on omega between 0 and s.
T plus s, you mean, I guess.
Here?
Yeah.
No, it's because I shifted.
You shifted like that.
Yeah. So I'm sorry, you're right.
Yeah.
Thank you.
That's too
No, you're right. That's the t plus s.
Okay.
Okay, and so what you see here is that these maps are depending on chunks of omega. We think of omega, it's the Wiener measure is sort of an independent product of omega continuously in time. This chunk is independent from this chunk. So typically when you have an RDS over something like this, which has all this independence built into it, you're thinking of this as a random composition of maps that are all independent. So no matter how I decompose it, it's just independent compositions of maps.
Because you got a white noise, right?
It's because of white noise. Yeah, that wouldn't hold if I did a more correlated time noise. So this is a feature of stochastic PD with white noise and random stochastic differential equations in general. And so this is a way of seeing the Markov property in general. Okay, so so actually under this condition on the Navier-Stokes equations, this is an example of a model under which all of the theorems hold. Okay. Now to prove that, you have to prove a lot of other properties of Navier-Stokes equations, which I don't have time to talk about today, but we'll mention in the next lectures. Okay. I think maybe I'll finish with just mentioning one more thing. These equations, I can do many other things. So it's not just special to 2D. You can do 3-dimensional if you're willing to put hyperviscosity or something. So as long as you're willing to work within subcritical equations, it's totally fine. And I'd say from a dynamical standpoint, I mean, it's hard to see the difference between a hyperviscous Navier-Stokes and just a purely viscous Navier-Stokes from looking at simulations. Of course, the regularity theory is much different. But if I'm willing to work in a setting where I have long time solutions and I have unique stationary measures, then any equation like this I can get should be a reasonable model to study. As Bjorn mentioned, I can also study an equation that is decidedly very non-chaotic, which is just the stochastic Stokes equation. In which case everything is just very sloshy and slow, but this one will also have Lagrangian chaos and mixing. So this is important to realize because as an Eulerian equation, this thing has all negative Lyapunov exponents. And so it really should disentangle the fact that chaos or the chaotic motion of the fluid is not responsible for chaos of the Lagrangian flow. But the other things you can consider is if I take any finite dimensional truncation of this equation, it will also work. And in fact, you can make the noise much weaker. You don't have to force all the modes in that case, because you can really use hyperelliptic theory.
Sorry, when don't you have to force all the modes yourself?
If you do a Galerkin truncation.
Okay.
An arbitrarily high Galerkin truncation, cut it off at 1 billion modes, and then I can force only 2, and all the stuff works.
And that's a finite dimensional system.
It's a finite dimensional system, yeah. So it's just a stochastic differential equation. But I mean, if I take Stokes, for instance, and I start it with only a few modes, that's essentially only finite dimensional as well, too. Yeah, okay, so I think that's all I can say in this time.
Questions?
So where else is like a simpler setting where existence of an RDS is known? Like does it make sense to say on the advection-diffusion equation, if you add noise, there's an RDS? And that is much simpler, I suppose.
Yeah, it should be simpler in that case, because I mean, for advection-diffusion is linear too. I think it should be much easier to get the existence of an RDS. So for instance, that solution operator that I'd written before S or ST, depending on the velocity path. This is a well-defined RDS over any shift on the velocity, but if I also do a stochastic velocity field, or something even that's white in time, I can also construct an RDS for that. And that's sometimes known as the Craigman model. But that's also fine to do, yeah.
And also like even without any randomness, that is also like technically an RDS.
Okay. Yeah, in that case, it's easy to say that it holds for all because there's only one path, or some finite number of paths potentially. But yeah.
And is there anything that can be said about that when you vary the viscosity? Or like what happens to the phi as you vary viscosity?
I don't know. Yeah, I mean, no more than I don't. Than what happens to you as you vary viscosity. I mean, I think like in terms of the image, anything you expect to happen to a solution of Navier-Stokes is you vary viscosity. What happened to phi? But I mean, I suppose if I take the derivative of this thing, then that's solving linearized Navier-Stokes. And there, I mean, yeah, I'm not 100% sure what is even known about that apart from, I mean, what's known. I don't think, I guess my point being that I'm not sure there's that much known better about this random dynamical system if there is noise than without noise, apart from the ergodic theory. So there's a little bit maybe you can say, so it allows you, for instance, you can construct random attractors in the same sort of way you can get finite dimensional attractors for this equation. You can do the same thing in this setting. But I think essentially it's only the ergodic theory that is the huge benefit. There was hope that you could do more, but as far as I know, I don't think there's anything.
So one thing that's kind of also included in this theorem is just the global repulsiveness, right? For the stochastically forced one. Can you maybe say how difficult this is? Because I guess you destroy the monotonicity for a little bit. So how do you get like global existence?
So I think it's not terribly hard if you use so let me think the right way to phrase this. So you can work path by path at this level, especially if you think about integrating my parts. So I can think I can just fix a Brownian path, and then it's like I'm just solving Navier-Stokes for a fixed path. So in the case of doing mild solutions, if you're comfortable enough with working with the mild form and then using sort of typical semilinear estimates that you would use for constructing mild solutions for 2D Navier-Stokes in the Hermsted case, I don't think there's that much more you have to do to construct global solutions. You have to estimate the regularity of this. And that there's a bunch of work. This has been done to death, for instance, in Deprado and Zabchik. They've worked on it very carefully. The more subtle things that you have to estimate are so I told you this thing depends only on this path between this. So this is an adaptedness statement. That's a little bit more work to show. And then fully constructing the RDS is a lot. Of course, once you do this, if you want to get any other higher regularity estimates, it becomes a pain because you have white noise and you have to do Ito calculus, which is okay. It's not that hard, but yeah, it makes a mess. It just makes everything uglier.
So do I understand correctly? Essentially, you're saying that once I am in a regime from which I have the classical well-postness of the BD, because
with additive,
then it takes care of the SH.
Yeah, essentially, I mean, if you have additive noise like this, you can especially in this kind of a setting where I have the smoothing, and I can essentially work with path by path. If I have multiplicative noise, where things here depend on the solution again, then it's not so easy. You have to work a little bit more carefully, I think.
Okay, there doesn't seem to be any other questions, so thanks.